If you look at the brain of a modern large language model, an LLM, it's just an incredible machine. It's processing these mountains of data, but it faces this fundamental internal trade-off every single second. Whenever it gets a prompt, it has to decide. Does it need to start thinking deeply, running complex calculations from scratch, or is this just a simple static fact that it should have memorized, like a flashcard? You send us sources about how to make AI smarter and, crucially, more efficient. And today, we are diving deep into a technical paper that offers a really elegant answer to that trade-off. It introduces something called Engram, a dedicated piece of architecture designed to give the AI that exact lightning-fast flashcard system.
And that's our mission today. Understanding how Engram fixes this massive inefficiency that's baked into the current state-of-the-art models. Right now, the favorite architecture is called Mixture of Experts, or MOE. And MOE is fantastic for scaling up capacity. It uses what's called conditional computation. It only turns on specific experts or sections of the model for complex dynamic logic. But here's the flaw. When that same MOE model needs a simple static fact, it still has to use those complex computation experts. It's forced to essentially simulate retrieval. It solves a mini puzzle every single time just to get an answer it should already know. And that simulation just wastes enormous amounts of time and processing power.
So if MOE is conditional computation, using the right brain cell to do the complex thinking Enneagram is introducing conditional memory, using the right memory bank to do the fast lookup. It's all about specialization. Okay, let's unpack why this duality matters so much. The paper starts by identifying this core linguistic duality. When we use language, we're basically doing one of two things. On one hand, you have compositional reasoning. This is the hard stuff. Figuring out novel logic, synthesizing arguments, creative problem solving.
And on the other hand, you have simple knowledge retrieval. These are just static facts, names, dates, common idioms, things that are fixed. Ideally, an LLM should handle the first task with deep computation and the second one with an instantaneous lookup. But that's not what's happening right now, the current transformer architecture.
Yeah.
It just lacks a native mechanism for that instantaneous memory lookup. So the whole network has to work hard for both tasks.
And the cost of this is high, and it hits, well, surprisingly early in the process. The source material gives a really clear example. If an LLM has to recognize a common entity, say Diana, Princess of Wales, the data shows the model currently has to expend computation across multiple early layers of attention and feed-forward networks.
We need to slow down on that point because it's absolutely critical. The paper calls this the expensive runtime reconstruction of a static lookup table. To really get why this is bad, you have to understand a concept called sequential depth. Think of sequential depth as the number of processing layers the AI has to pass through, one after another, before it gives you an answer. That depth is your most precious limited resource. If you waste the first few layers just simulating the retrieval of Diana, Princess of Wales, those layers can't be used for complex reasoning later on. It's like forcing yourself to recalculate 2 + 2 = 4 using calculus every single time you need it in a math problem.
Right, you need that 2 + 2 flashcard so you can free up your brain to tackle the differential equation.
Exactly.
So the whole goal is to stop wasting our early, valuable processing steps, our sequential depth on static knowledge.
Which brings us to Engram. Engram is that conditional memory module, and it's actually built on a foundation of existing linguistic ideas. It modernizes the concept of enneagrams, which traditionally just capture local context, predictable word patterns like how the great almost always follows Alexander.
I wonder, though, is this just repackaging an old idea, or is there some genuinely new magic here that makes it work at this massive scale?
That's a great question. The magic isn't just the idea of local context. The magic is twofold: the size of the memory bank and the speed of access. Engram creates this massive embedding table, which is basically the physical memory bank. And the key technical innovation is how fast it accesses that bank. It uses a constant time lookup mechanism, which they label as O1 lookup.
Okay, O1, for anyone less familiar, can you just quickly break that down?
Sure. The O notation just measures how long it takes to find something as your dataset grows. So searching a huge phone book by reading every single name would be ON. The time grows with the number of names. But O1 means the time taken is constant. Doesn't matter how big the list is. Imagine finding a word in a 1,000,000-word dictionary just as fast as in a 10-word dictionary. That's the key. That scalability is vital.
That instant access means we can scale this memory bank into the billions of parameters without slowing down the core processing speed. And here's where it gets really interesting for me. When we look at what the system actually chooses to remember, They showed these visualizations of Enneagram's activation. It strongly activates on multi-token named entities like Alexander the Great or the Milky Way, where the words are super predictable together. It also grabs formulaic phrases like, by the way. This really confirms it's grabbing those static, memorizable blocks of language.
And importantly, this isn't just an English thing. The case study showed Enneagram activating successfully on Chinese idiomatic expressions and historical figures, like zhanghuishuai or the Four Great Inventions. It's proof that this memory function is fundamental to language, not just, one specific language.
So how do they keep this instant memory bank organized and error-free? If it's pulling information that fast, how do we make sure it pulls the right thing?
That takes two crucial engineering layers. First, they use something called tokenizer compression. The standard vocabulary can be like 128,000 different tokens. They reduce that by 23%. And this isn't just about saving space, it's about semantic density. By collapsing equivalent terms, like grouping the capitalized apple with a lowercase apple, they make sure the memory bank maps to actual concepts, not just different ways a word might be spelled or tokenized.
So it makes the memory bank smarter.
Exactly. And the second piece is context-aware gating. This is the quality control. So if the system retrieves a memory, say the word bank, because it shares a hash with riverbank, this gating function checks if that memory actually fits the current context. If the retrieved memory contradicts the context, the gate just suppresses it. It minimizes noise and errors from hash collisions.
That's brilliant engineering. But anytime we introduce a massive new memory block, I have to imagine it creates a fight for resources, right? We've already got the MOE experts taking up space. So how do they balance this dedicated memory against the dynamic processing power?
You've just hit on the core challenge. The paper labels it the sparsity allocation problem. Given a fixed total budget for the AI's parameter count, how do you optimally divide that budget between MOE, which is your conditional computation, and Enneagram, which is your conditional memory?
And this is where the researchers moved past just intuition and found a clear, measurable rule. They uncovered a U-shaped scaling law, which means you can't just maximize performance by going all in on one side or the other.
Precisely. If you're pure MOE-so, 100% of your budget on computation, you get suboptimal performance. You're wasting power simulating retrieval. But if you go the other way and become Engram dominated, all memory, no thinking, you lose your dynamic reasoning, you have a huge library, but no one's smart enough to use the books.
So there's a sweet spot.
A very consistent sweet spot.
Yeah.
They found that reallocating roughly 20% to 25% of the sparse parameter budget away from MOE and toward Engram's memory consistently gave the best performance. This is the scientific proof. The two modules are not substitutes. They're fundamentally complementary systems that thrive when they're balanced.
And because of that O1 constant time lookup we talked about, the researchers could push the memory size even further. They experimented with what they called the infinite memory regime.
Yes, and this is wild. They aggressively scaled the Enneagram memory. They added up to 13 billion parameters in one experiment and saw something fantastic. Performance improvement just followed a predictable power law. The bottleneck completely shifted. Since the retrieval speed never changes, you can just keep making the memory bank larger, and the model continues to get smarter, predictably, without hitting some technical limit on access time.
So we know Enneagram is more efficient, but let's talk about the big breakthrough. Why does having a dedicated flashcard system suddenly make the AI better at thinking? The results go way beyond simple rote memorization.
This is the non-obvious part that makes the paper so important. By taking over all the repetitive static tasks like that Diana, Princess of Wales, lookup Enneagram relieves the backbone of the model.
Okay, what does that mean, relieves the backbone?
Think of it this way. If the first 7 processing layers are no longer worried about recalling basic facts, those layers are instantly freed up. They can immediately start the complex work of synthesis and logic. Enneagram makes the underlying neural network effectively deeper for that compositional reasoning.
And we can see that impact directly in the benchmarks. When they compared the Enneagram 27B model to an identically sized pure MOE model, Enneagram showed these surprising, significant gains, not just in factual recall, but in general logic. We saw huge improvements in general reasoning. BBH improved by 5.0 points, ARC challenge by 3.7 points, and even more impressively, it boosts capabilities in domains that need complex step-by-step logic, like code and math. HumanEval, which is a coding benchmark, gained 3.0 points, and the math benchmark gained 2.4 points. This is proof that the efficiency gain is translating directly into higher cognitive function.
Absolutely. And there's a critical side effect here that's related to context. If Engram handles all the local dependency modeling, the simple phrases and predictable patterns, it frees up the attention capacity of the main network to focus on the global context.
The big picture.
Exactly. The attention mechanism isn't cluttered with all these local details anymore. This gives the model a kind of long context superpower, which is crystal clear in the results. One benchmark, multi-query NIAH, which is designed to test long context retrieval, jumped from a respectable 84.2 all the way up to an astonishing 97.0. The memory bank helps the model see the forest, not just the trees.
So the researchers couldn't just tell us the model was getting deeper. They had to prove it was happening internally. They ran 2 very specific tests. And these sound pretty technical. Let's try and break down how they work so we can understand the smoking gun evidence. What was the first test?
The first one used a technique called Logit Lens. Essentially, Logit Lens lets you peek inside the model at different layers and see how quickly it reaches a high-confidence, valid prediction. It measures divergence, how much the model is correcting itself. The results showed the Engram models had systematically smaller divergences in their early layers. They were prediction-ready much sooner because they weren't struggling to recall facts. The second test was the twin models test, using CKA analysis. CKA is a sophisticated mathematical way to compare the internal representational structure, sort of the neural fingerprint of 2 different models. It tells you how similar their thinking process is at specific layers.
Okay, so they compared the Engram model's fingerprint to the standard MOE model's fingerprint. And what did that comparison show?
This is the smoking gun that confirms their whole hypothesis. They found a distinct upward shift. The representations, or the thinking patterns, formed at layer 5 of the Engram model, aligned most closely with layer 12 of the MOE baseline.
Whoa, so the Enneagram model is functionally getting 7 layers worth of thinking done almost instantly just by offloading the memorization task. It is structurally deeper.
It is. And finally, they ran the ultimate functional test, the sensitivity analysis, which they can just call the flashcard test. They ran the model, but they completely suppressed the Enneagram module. They told the AI you can't use your flashcards. And the results showed a perfectly clean functional dichotomy.
What happened?
Factual knowledge benchmarks like Trivia QA suffered a catastrophic collapse. They retained only 29% of their performance. If Enneagram is turned off, the facts disappear. It proves Enneagram has become the primary, dedicated knowledge repository.
But the dynamic tasks, they remained largely intact. Reading comprehension tasks, which rely on contextual understanding of the text in front of it, not rote memorization, were remarkably resilient. They retained between 81% and 93% of their performance. This just cleanly proves that separation of duties. The backbone still handles the context-grounded tasks, while Enneagram handles the static facts. So what does this all mean for the future of building these massive AIs? The final aha moment for you, the listener, is that Enneagram offers a path to scale AI size without needing prohibitively huge and expensive GPU memory.
This is maybe the most practical benefit. Remember how we said Enneagram retrieval is deterministic? Unlike MOE, where you don't know which expert you'll need until you're there, Engram's memory indices are known before the computation even begins. That predictability is the key.
And that lets you plan ahead.
It lets the system use a prefetch and overlap strategy. Since the lookups are predictable, the system can offload those massive embedding tables, we're talking hundreds of billions of parameters, to cheaper, slower host memory like CPU memory.
So while the high-speed GPU is busy calculating the current layer, the system is already fetching the memory needed for the next layer's Enneagram lookup in the background. It's like having 2 teams working at the same time.
Precisely. You overlap the slow memory fetching with the fast computation, and the infrastructure cost is incredibly low. This whole process incurred a negligible overhead, peaking at only a 2.8% time penalty on the smallest 8B model. Enneagram effectively bypasses the traditional bottleneck of GPU memory, letting us expand the model's total knowledge base almost infinitely and affordably.
Enneagram is a genuine breakthrough then. It establishes conditional memory as this indispensable modeling primitive. By giving the AI a dedicated fast memory function for static facts, it simultaneously frees up the neural backbone, making complex reasoning deeper and long context handling significantly stronger. It's like giving the student a perfect set of flashcards so they can spend all their study time on critical thinking.
And this concept of dual sparsity. So conditional computation from MOE for dynamic logic and conditional memory from Engram for static knowledge. This is clearly redefining how we're going to build next-generation sparse models. They're structurally, functionally, and efficiently complementary. And this leads us to the final provocative thought, which is hinted at by the structure of language itself.
The sources remind us that natural language patterns follow a Zipfian distribution. A few facts and phrases are used constantly, and a vast number of facts are used very rarely. So if this massive Engram memory bank can be organized into a multi-level cache, very fast, premium memory for the common facts, and slower high-capacity memory for the rare ones, how much bigger and faster can AI models become while keeping hardware costs manageable? We are now building AIs where the line between perfect memorization and true intellectual understanding is not a blur, but a clearly defined scalable architectural choice.